IEEE APS student chapter at the University of Toronto. And we have our website here that you can check it out. We usually post the events in advance on the website. And since we are being sponsored by IEEE APS, I would like, on behalf of the chapter, I would like to ask you to consider joining and becoming a member of IEEE and APS Society. There are definitely a lot of benefits. You can apply for grants for conferences. You can basically have access to many journals. And you can definitely check these benefits on our website for more details, or you can contact us if you have questions. And I think that is it all about IEEE and our chapter. Actually, besides the technical events that we organize, we do organize some local events that are non-technical, such as getting together for newcomers so that they can get familiar with the grad life at U of T. And also, like, we are going to have an alumni event soon. So if you're joining from U of T, definitely check those out and try to attend them. And thank you very much. Yeah, I think that's it. So we can wait a little bit so that if more people want to join, they can do that. And then I'll start with introducing our speaker, Dr. Sajjad Taravati. Okay. Maybe, yeah, we can wait 2 more minutes. I think whoever wanted to come, they already joined.
Yeah, are you, I can't see the waiting room while I'm full screen.
I don't think we have anybody in the waiting room. So maybe
okay, cool.
we can so this, this talk will be recorded, and then it will be available on our YouTube channel soon after the talk. So if you don't understand something or you miss something, you definitely can check that video out. We usually try to post other videos on that channel as well. So if you want to subscribe to the channel and basically know what is going on, you can check that out as well. But definitely we will post the videos that are cool with the speakers.
Parnaz, what is the YouTube channel?
It's let me show you. Actually, I should post that. Let me see. I think it has the name IEEE U of T APS in it, but I'll check it here. Yeah, IEEE U of T APS chapter. Such a long name, but let me see if I can share it here with you. You already have one.
I was going to say maybe we can put it in the link in the chat.
Oh yeah, sure.
In the chat, yeah.
Yeah.
I think we also have that link on our website, probably.
Yeah, we
and
have.
If it's not
one...
there, we'll make sure we put it there.
Yeah.
Yes. No, I think I posted the link for one of the videos we already have there. Okay, I don't know how to share this, but I'm going to.
If you click on chat, then you can just paste it there.
No, I don't know which. Okay, see if this would work. If this would just go to the channel, I think it would go to the channel. But we already have 6 subscribers. Join us. Okay, so let me start by introducing our speaker. So Dr. Sajjad Taravati received his PhD degree in 2017 in electrical engineering from Polytechnique Montreal, Quebec, Canada, where he was conducting research on non-reciprocal magnetless electromagnetic systems and analog signal processing. From 2017 to 2018, he was a postdoctoral fellow in the group of Professor Ahmed A. Kishk at Concordia University, Montreal, Canada. And there he was doing research in the field of electromagnetics, non-reciprocity, and space-time modulation. He's currently a postdoctoral fellow at the University of Toronto, Canada, and his current research interests include non-reciprocal magnetless system, space-time modulated structures, electronic circuits and systems, broadband phase shifters, wave engineering. Dr. Taravati received the Khwarizmi International Award in 2010 and the Outstanding Researcher Student Award of IUST in 2012. In 2018, he received the Horizon Postdoctoral Fellowship and the Graduate Student Award, both from the Concordia University, Montreal. Dr. Taravati is now the technical advisor at Lattice Intelligence, a startup company that is supported by the well-known startup incubator, Tandem Launch Inc., and is established based on two of Dr. Taravati's research work on versatile and programmable space-time metasurfaces. We are very excited to have Dr. Taravati here today with us, and very excited to hear about the space-time metasurfaces. Thank you.
Thank you so much, Farinaz, for organizing this, and it's a great opportunity for me to present our work on space-time metasurfaces in general, non-reciprocal metasurfaces. I'm happy to see Mr. Gersimran Sethi. He's in the industry part and he's very active. He was in U of T and he's doing a great job in the industry part. So I will present the academic part a little bit, both in theoretical analysis, simulation, and implementation of space-time metasurfaces, and then I will, at the end, I will talk about the industry commercialization and implementation of the structure. So space-time metasurfaces have won great attention in the academia as well as industry. And so they have shown to be excellent devices for manipulation of electromagnetic waves. So they are compact and they're active and they can manipulate the electromagnetic waves in a versatile manner. And today I will show you some of the applications of this space-time metasurfaces and the future directions. My name is Sajjad Taravati, and I'm a postdoctoral fellow at the University of Toronto, as actually laid out by Farinaz. Here is the outline of my presentation. I'll first give an introduction about the space-time actually interfaces and the Minkowski diagrams and the essence of the work. Then I will talk about sinusoidal space-time modulation. This is the most useful type of space-time modulation. And I will provide some of the recently proposed applications of space-time sinusoidal modulation. In general, I will show you pure frequency converter, space-time metasurfaces, non-reciprocal metasurfaces, as well as transistor-loaded space-time metasurfaces. These are different types of applications of space-time modulation, and I will provide the details later in my talk. So metasurfaces are compact structure that engineer electromagnetic waves through a specific boundary condition rather than constitutive parameters of a 3D space, which we had in metamaterials and natural materials. So basically, their thickness is sub-wavelength and they are very compact structures. They could do lots of things to the incident wave. They could change the momentum of the incident wave. They could change the energy of the incident wave. And they could change the phase of the incident wave as well, and so on and so forth. And they are quite powerful, and you could use them for engineering our electromagnetic waves. However, we were using passive metasurfaces in the past, and recently there has been a surge of interest on active metasurfaces. In general, you could use space-time metasurfaces and as well as transistor-loaded metasurfaces as active structures, and it can be shown that these active metasurfaces have much more, stronger capabilities and functionalities than passive conventional metasurfaces. Here, for example, is like a particular case that we see the incident wave is at omega in, and the reflected wave is at omega in plus omega. So which is like a frequency converter metasurface. There are other groups that are working on a space-time metasurfaces. For instance, there's Professor Shadrivov, there's Professor Chui at Southeast University of China, and there's Professor Gerbish at the University of Michigan. They are working actively on space-time metasurfaces, and they have done great works. There's also Professor Musallai in Northeastern University, which is working on optical space-time metasurfaces, and I could also name Professor Gomez Diaz at the University of California. Also, I mean, there are several groups. There's Professor Shang-Hui Fan at Stanford, Professor Harry Atwater at the Caltech, and so on. So it's quite a hot topic, and very prestigious groups around the world, US, Canada, they are working on this topic to come up with some exciting and useful applications and functionalities. So today I'm going to present you some of the work that we have done over the past few years on this topic. The Minkowski space-time diagram is a very useful tool for understanding and analysis of wave propagation in a space-time. It's constituted of two cones where the apex is light at the present, and you have past and future, and so basically any discontinuity in this space-time diagram results in backward and forward waves. The Fourier transform of the Minkowski space-time diagram is a dispersion diagram that we are more familiar with. So here we have a K versus omega line. So the K vector is a wave number that could be a three-dimensional wave number, Kx, Ky, and Kz. And we have omega line that shows the frequency. So basically in this diagram, in the right side, we could have a subluminal, superluminal, and luminal waves. The subluminal wave is propagating slower than the speed of the light, while the superluminal wave propagates faster than the speed of the light, and luminal wave propagates as fast as the speed of the light. So this is very important, and it can be shown that using this dispersion diagram, especially in a space-time modulated structures, that we have a periodic dispersion diagrams. So it's very useful to apply this dispersion diagram to understand the propagation of the wave inside the medium. Otherwise, it would be very hard. And also, if you want to come up with some new ideas in a space-time medium, so it's good to just consider the analysis of the space-time diagrams, space-time dispersion diagrams, to see what is happening inside the medium. So I could say in a space-time medium, it's nearly impossible to analyze the wave propagation without looking into the dispersion diagram of the medium. So I mean, later in my talk, I will elaborate on the dispersion diagram of the space-time modulated media, especially the sinusoidal ones, and show you how we can actually analyze it. First, let's talk about the spatial interface that we are more familiar with. So it's a spatial interface. So there is a discontinuity in space, and as we all know, once we have a discontinuity in space, we have a forward wave, which is shown with T, and we have a reflected wave which is shown with R. So we have the reflected wave goes back toward the minus Z direction, while the transmitted wave goes toward the plus Z direction. Here, since we have a spatial interface, the K vector, the wave number changes, as you see here, but the omega, the temporal frequency is constant. However, if we have a temporal interface, the wave number remains constant, while the temporal frequency omega changes, which is actually the opposite of a spatial interface. Still, the reflected wave reflects back toward minus Z direction as what we had in a spatial interface. However, the reflected wave reflects back inside the actually second medium, as you see inside the green medium. This is very interesting, and has lots of applications. Once we analyze the wave incidence to a space-time interface, it would be much more complicated than the two latter cases. As you see, we could have a reflected wave inside the second medium or inside the first medium. It depends on the velocity of the interface. So if the velocity is faster than the speed of the light, so we are closer to the temporal interface, and the reflected wave is inside the second medium. However, if we have a subluminal interface, the reflected wave would reflect back in the first medium. And also, if we are going to find the temporal and the spatial frequency K and omega inside the second medium, we have to apply much more complicated formulas to find out what is the exact number of exact value of the wave number and the temporal frequencies. So it's a quite research topic of interest, and yeah, you could have different applications. For example, Professor Nader Enqeta at the University of Pennsylvania, he's working on these temporal interfaces, and you could have lots of good applications, and they are quite interesting, both from analytical point of view and application point of view. However, as I said, the most useful type of space-time modulation is a sinusoidal one, or I could say a periodic one. You could use a sinusoidal or perhaps other types of periodic types of waves. Here you see that the permittivity of the medium is changing in a space and time. This shows the profile of the permittivity, as you see, is shown with epsilon that depends on the z space and t time. Here, beta m represents the wave number, the modulation wave number, and omega m represents the temporal frequency of the modulation. So these two are actually related to each other to gamma, which is the space-time velocity ratio. This is quite important, and with changing the gamma, the relation between the beta m and omega m, we could have different types of space-time modulation. As I said, if gamma is smaller than 1, we can have a subluminal space-time modulation, and if the gamma is larger than 1, we can have a superluminal space-time modulation, which shows that the space-time modulation is close to a temporal modulation. So the spatial modulation is quite small. So, I mean, for different applications, we could have different types of gamma space-time velocity ratio, and it can be shown that, I will show that with such actually playing or like manipulating the gamma, we can have different applications, different physical phenomena in this space-time modulation structures. Here, since the actually permittivity is periodic in both space and time, it can be shown that this permittivity can be represented based on the Fourier series expansion, as you see here in the bottom. So both permittivity, permeability can be represented in terms of Fourier series expansion because they are periodic. In general, we could have a space-time modulation of permittivity or permeability, or even conductivity and so on. So you could have different applications for each of them, and the most useful one is the permittivity because it's very easy to fabricate and realize it in practice. Because as I will show, you could realize it with, for example, varactors, but the permeability one, mu, is a bit difficult, but it was shown in the past that this could be realized as well. And as I said, other groups like Professor Harish Krishnaswamy, they are working on the modulation of conductivity as well. So it's quite various and interesting, and you could have different applications for each modulation. So basically what we do is that first we represent the space-time permittivity based on the Fourier series expansion, and then insert it into the Maxwell equation. And then again, since the structure is periodic in space and time, we could represent the electromagnetic field based on the Fourier series expansion, a double Bloch fluid solution, and put it inside the Maxwell equation and find the unknown coefficients of the electromagnetic waves inside the structure. once you have it, you could apply the boundary conditions and get the wave outside the structure. This is like a very, I mean, a strict way to find out the scattered wave inside and outside the surface and the structure. We have a space-time modulation in nature as well. For example, here you could see that flying an airplane on top of an ocean, it could actually create amplification of the water waves and create a space-time modulation of the water waves, which is very interesting. Also, we have it in the tsunami that you see that earthquake on the bottom of the sea can result in a very strong water waves that are propagating toward the shore. So here you see that, for example, the water waves are propagating unidirectionally. As also what we see here in the left airplane case that we see, always they are unidirectional, and this is basically the characteristic of the space-time modulation. Since the modulation is unidirectional, we would have a non-reciprocity. So, and it's very interesting. And also, if you just take a look at this, the right figure that shows the tsunami, you will see that this wave has different frequencies. In general, we have I could say three interesting phenomena in the space-time sinusoidal modulation. The first is frequency generation. Second is the non-reciprocity and unidirectionality of the structure. And the third one is amplification. What we see here, for example, in the left side, that we have the water waves are amplified. So these three are very interesting, and over the past decades, there have been several applications of this based on these three phenomena in space-time modulated structures. To show you how to realize it in practice, I would like to first show you an equivalent circuit of the transmission lines. So this is a uniform transmission lines that we are more familiar with. So, for example, I chose a microstrip line, and on the bottom you see that this structure, this microstrip line, can be modeled by inductors and capacitors, as you see here. And so they're all fixed. We have L naught and C naught that show the intrinsic capacitance and inductance of the microstrip structure. And so they're periodic. Here, to realize a space-time modulated medium, we just use a shunt capacitor and put it in parallel with the C naught inside the medium like this. And so this capacitor is variable, and it can its value can be varied based on the voltage of its two nodes. And so we use a RF bias. Here it's shown with Vm cosine of omega mt, which is varying in time and propagating along the z direction, which is creating a space-time varying RF bias, Vm cosine of beta n z minus omega mt. So basically, we have an RF bias which is propagating and spatiotemporally modulating the capacitors. And it can be shown that this creates a permittivity of what I've shown here, actually, epsilon naught multiplied by epsilon r, 1 plus delta epsilon cosine of beta m z minus omega mt. Here, delta shows the amplitude of the modulation. If we have a stronger RF bias, we would have a stronger modulation amplitude. For different applications, we might be interested in a stronger or weaker space-time modulation. It's quite, I mean, it depends on the application and what we are going to achieve. But so basically, these are what we are going to use in the design of our structure. That I will show you that for different applications and for different apparatuses, we could have a different beta m and different delta e to make sure that the scattered waves are as what we want. So basically here, I've shown this with permittivity epsilon, but it's a dual of a capacitor. We know that in electromagnetics, the capacitor is equal to permittivity multiplied by a constant function. So I mean, it's the same thing. So permittivity or capacitance is the same thing, and we can have the same phenomena using permittivity in electromagnetics or capacitance in signals and in voltages. So we use varactors, variable capacitors, as shown here. So they basically the voltage of the capacitance of the variable capacitor can change based on the changing the voltage of its two nodes, as you see here. if we increase the voltage, the capacitance of the capacitor decreases and so on. And so basically this is what we do in practice. So we use varactors to realize this. But as I said, you could have different structures. For example, it can be shown that you can have a variable inductance as well using varactors. I mean, there are quite a few papers that shows that you could have a variable inductance using varactors. And so this is also like a research that if anyone is interested, can look into that. So for example, it has been shown that if you just modulate both inductance and capacitance, you could have different physical phenomena, and it's very interesting, and so on and so forth. So whatever you think about this structure, that I mean, it's so it could be a new research topic. So it's quite like powerful in terms of physical phenomena. And if you change something, for example, you could have different capacitances at different places, and it provide a aperiodic or non-uniform space-time modulated structure, and so on. So here is like a fabricated structure that shows we have a CPW coplanar waveguide that is modulated in a space and time. We have a series connected varactors, and from the engineering part of point of view, so we should have the distance between the varactors should be sub-wavelength to make sure that we are evaluating the exact space-time modulation that is continuous. And as you see here, we have a duplexer here to feed both the RF files for the space-time modulation as well as the incident wave. Again, for each application, you could have different scenarios. But let's go through this dispersion diagrams, which is very important for the analysis of the space-time modulation. Here, you see the dispersion diagram of a uniform medium. We all know that the dispersion diagram of a uniform medium is formed by two cones. Their apexes are laid at the omega equal to 0. And as you see, forward and backward waves are characterized by positive and negative group velocities respectively. And you could analyze the wave propagation in these structures in the uniform medium based on the analysis of the dispersion diagram. But if we go to a space-time modulated medium, since the medium is periodic in both space and time, the dispersion diagram is formed by a periodic set of cones. And as you see, their apexes are laid in an oblique line, which is the slope is equal to omega m divided by VB, which is here Vm is equal to modulation velocity, and VB is equal to velocity of the background medium. So it can be shown that with changing the gamma space-time velocity ratio as well as beta, we could have different set of periodic cones, and the wave propagation inside the medium would change as well. So I just wanted to show that for this structure, the dispersion diagram is periodic and is also oblique, and we should just achieve the dispersion diagram for each space-time medium to make sure that we understand the wave propagation inside the medium. For example, here is an analytical solution for the space-time dispersion diagram of a luminal, actually, a space-time modulation. As you see, the cones are very close to each other. In the left side, you see the dispersion diagram that the forward waves, they're actually very close to each other, while the backward waves are separated from each other. And this shows the non-reciprocity of the medium because the forward waves are close to each other and then they can couple to each other, while the backward waves are as far as what we can have, and they cannot couple to each other. And here in the right side, in the top, you see the isofrequency dispersion diagram of the medium. As you see, for example, here for the gamma equal to 0.3 and for the gamma equal to 0.7, I guess. And as you see, the distance between the circles are different in these two cases. So basically, these are on the top. We have isofrequency dispersion diagrams that shows the kx versus beta, which is beta here is the kz, and on the bottom we have basically dispersion diagram which is omega versus beta. It depends. If we have an oblique incidence to the medium, we could for sure analyze the isofrequency diagrams because the kx is non-zero. But for the normal incidence, in several cases, we could have a normal incidence to the medium. We don't need to analyze the isofrequency dispersion diagrams, these circles, because the kx is zero, and we just need to analyze the omega versus beta dispersion diagram. To get the solution inside and outside the space-time medium, we just consider the transmitted and the reflected waves. Basically, it can be shown that each incident, each reflected and transmitted wave includes different frequencies, and basically, so some of them are propagating along the boundary condition, which are called the surface waves, and some of them are propagating normal to the boundary of the structure. And so there is like a setup of frequencies, and as we go further to the boundary of the structure, the frequencies become higher. So basically, it can be shown that each frequency is scattered at a specified angle of reflection and transmission, and also with different amplitudes. And this is quite interesting. And on the bottom, you see the formula for the angle of reflection and transmission. And so it depends on the frequency of the modulation and incident angle. To analyze the structure, one of the interesting and useful tools is FDTD simulation of the structure. In general, there are softwares that can simulate this space-time modulated media. There is a COMSOL multiphysics that you can use to simulate these structures. But you could also implement your own FDTD code to make sure that you understand the wave scattering from the structure. Here, for example, you see the structure and scheme of the FDTD code that I implemented in the past. So basically, we have discretized the medium in space and time, and just iterate the FDTD and the solving of a Maxwell equation to get the desired scattering of electromagnetic waves inside and outside the structure. And here you see the result of the FDTD simulation. For example, here you see the basically transmitted wave for different amplitudes. On the top, you see amplitude equal to 0.15, and also the bigger amplitude. And basically, what you have here, you see that when we increase the amplitude of the modulation to 0.4, we have a stronger frequency generation and amplitudes on top of the structure that shows that having a stronger amplitude results in a stronger frequency generation and in general a stronger non-reciprocity. On the bottom is like a zoom of the transmitted wave. As you see, each frequency is scattered at a specified angle of transmission. Smaller frequencies are transmitted horizontally, and larger frequencies are transmitted vertically, which is quite interesting. And as I said, it could have different applications for this physical phenomena. So, let's go to some of the applications. The first one is pure frequency converter space-time metasurfaces. Here I provide quite a few applications of pure frequency conversion in a space-time modulation media. The first one is this Antenna-Mixer-Amplifier structure. So basically, this structure is operating based on the surface waves. As I showed previously, you could generate a space-time surface wave that propagate along the boundary of the medium. Here, the structure is designed in a way that generates space-time surface waves. Again, as I said, you could do this by manipulating or changing the space-time velocity ratio, gamma, which corresponds to beta m, which corresponds to the ratio of the beta m and omega m. And you could have a transition from incoming propagating wave at omega naught to a surface wave at omega naught minus omega m. And in the transmission mode that you see on the bottom, we have a transition of the input wave, which is a surface wave at omega if, to a space wave at omega if plus omega m. So here we consider a very large omega m, which is larger than omega if, to have a practical actually transition and frequency conversion that we would like in real scenarios. Because in real scenarios, we would like to have a frequency conversion that is, changing the frequency of the incident wave from one band to another band, like from 1 gigahertz to 3 gigahertz, or like 1 gigahertz to 2.5 gigahertz. We need a large frequency transition to make sure that the incident and the transmitted waves are at the desired frequencies. And it can be shown that the operation of this structure is like this. We have a frequency conversion in the reception and transmission states, and we have amplification in the reception state as well, and the bandpass frequency, because here basically we have a pure frequency from a space wave to a surface wave that acts as a bandpass filter as well, because we have a very pure frequency transition, and we don't need any further filtering mechanisms. So quite interesting, both from the analytical and design point of view and practical point of view. Here, it can be shown that, as I said, by analysis of these isofrequency diagrams, it can be shown that the structure operates as I described previously. So basically, we have a complex wave number which includes imaginary part of the wave number as well. Here, imaginary part is shown with alpha of z, and also we have a real part of the wave number which is shown with beta. And also, as I said, we have different harmonics of the temporal frequency omega n. First, we just start from the Helmholtz equation that is shown here, and achieve the scattering angles for each space-time harmonic. And it can be shown that with the proper design of the structure, for example, we can achieve for a given theta I incident angle, we could have a surface wave which is basically scattered at 90 degree, which is the boundary of the structure. So we have a theta I transition from theta I to 90 degree, which is the boundary of the structure, and it shows the frequency conversion as well as antenna application, because here we have a surface wave which is coming to the medium. The medium is not an antenna per se; it's just a space-time medium. But here we show that it operates not only as an antenna but also as a frequency converter, which is very interesting, because when we just proposed this one, it was the first time that was shown that a space-time medium can operate as an antenna as well. So here is the numerical simulation results that you show a space wave with frequency omega naught is impinging on the surface of the medium, and is making a transition to a surface wave with the frequency omega if. It's apparent that the frequency of the incident wave and the frequency of the converted waves are very far from each other. So it shows that it's a practical frequency conversion, we have a large frequency ratio. This is for the reception state, the downlink, and also for the uplink transition. It provides quite a similar phenomena that shows we have a frequency up conversion from omega if to omega naught. That is the opposite of the downlink and reception state. So basically, it shows that the structure operates as an antenna, as a mixer, and as an amplifier, simultaneously. In the reception state, we have amplification. We have quite a small amplification, but in the transmission, we don't have amplification. But it's fine, because this is what we need actually in practical communication systems. We are more in need of amplification in the reception state. But yeah. And the second one is this Mixer-Duplexer-Antenna Leaky-Wave system. In contrast to the previous structure that I showed here, The structure is not a surface wave structure. It's a Leaky-Wave structure that is modulated in space and time. And the functionality of the structure is like this. We are going to have to make a transition from omega naught to omega 1, omega naught to omega naught plus omega m in the transmission state. And in the reception state, we are going to make a transition from omega 1 to omega 1 minus omega m. So basically, it's a three-port structure. It's a TX port, RX port, and antenna port. So it shows that a space-time medium can operate as a full transceiver that provides not only the mixing and radiation, but also the duplexing functionality, which is very, very interesting. So we don't need any circulator or duplexer in the structure, not a mixer in the transmission and reception state. And here is a fabricated structure. It is a Leaky-Wave structure that is modulated in a space and time using varactors, and we have two filters in both sides of the structure to make sure that the undesired space-time harmonics are suppressed. And here is the results for the experimental results for the uplink that you see. We have a beam that is changing based on the frequency of the modulation. So basically, this is the characteristic of the Leaky-Wave antenna. So in Leaky-Wave antennas, you can change the angle of radiation using the frequency of the Leaky-Wave structure. Here, interestingly, we see that we can change the angle of radiation using the modulation parameters, which is very interesting. So you don't need to change input frequency. Input frequency is fixed, but you could have a full space or half a space beam steering using through changing the modulation parameters. Same thing for the downlink, and you see that for the downlink, the wave goes to the port, to the RX port that we would like, and very small part of the wave goes to the TX port, and this is due to the non-reciprocity of the structure that I explained previously, and so it's very interesting. And we have a frequency generation non-reciprocity that we use in this structure, and the Leaky-Wave characteristic of antenna help us to realize this functionality. And the third one is a pure and linear frequency converter metasurface that you see here. This metasurface provides both up conversion and down conversion. On the actually top case, so that you see the incident wave is blue. We have a omega incident, which is equal to omega naught plus omega m, is impinging on the surface of the metasurface, and it makes a transition to omega naught, which is a down converted part of the incident wave. You could also have an up conversion where the incident wave is at omega naught minus omega m, and the output wave acquires the temporal frequency of omega naught. So basically, it could provide both up conversion and down conversion depending on the actually frequency of this incident wave. And the concept is as follows actually. So basically, when you have a patch antenna, it can be shown that the structure provides a single resonant frequency. So you have a single transmission. Just imagine this, because here we have three resonances. But if you have a single patch antenna, you would have just one resonance. But when we just interconnect the two patches from two sides of the metasurface via holes, it can be shown that we could have at least three resonances that are based on the multiple reflections inside the structure, because you have discontinuity in the patches, and it provides and it creates different resonances, and we use these different resonances and this band pass and also the suppression in the stop bands to basically transmit the desired frequency and suppress the undesired frequency. As you see here, we have a strong stop bands. And this strong stop band can be used for suppression of the undesired time harmonics, and make sure that only the desired time harmonics is transmitted to the other side of the metasurface. Here is a fabricated structure. As you see, is a multi-layer structure. So basically, it's included of different unit cells. Each unit cell is composed of two patches that are interconnected to each other in two sides of the metasurface, and we have a basically modulation, RF modulation that is fed to the unit cells and provides the modulation signal to spatiotemporally modulate the varactors. As you see, each unit cell includes 4 varactors. This is just a scheme that I used. So basically, you could have different scenarios, maybe with 2 varactors if you wish, but you should make sure that the structure emulates the space-time modulation that we have in practice. So this is basically the best way that I found to do it, but there are other ways that other groups are using. So basically, from the engineering point of view, you could take a look in other papers. So yeah, I mean, you don't need to just stick to one scheme, but you should make sure that you are emulating a space-time medium and make a disconnection and isolation between the incident wave and the modulation wave to make sure that the modulation only feeds the varactors, not the other part of the metasurface. Anyways, this is the fabricated structure. As you see, is a 2-side metasurface, and the experimental setup, as you see. And here is the results. The top shows the up conversion that you see. We have a strong up converted wave, and you see that the undesired time harmonics are sufficiently suppressed. And on the bottom, you see the down conversion case that you see from I mean, the incident wave is at 5 gigahertz, and the down converted wave is at 3.3 gigahertz, I believe. And so it has a large frequency ratio between the incident and the converted waves. And it shows that we could have both up and down conversions using the single metasurface. So the bandpass and the bands of the metasurface can be varied using the space-time modulation parameters like frequencies and space-time velocity ratio and so on. And this is just a proof of concept, and in practice you could make it more advanced. Like you could change the frequency of the patches and make broadband patches to make sure that it provides broadband frequency conversion and so on. And so I mean, there is still a lot to be studied, and this is just the initial fabrication and results, but it's quite interesting. So the next physical phenomena that is very interesting in space-time metasurfaces is non-reciprocity. I already showed some part of the non-reciprocity, but in the following, I'm going to show you some practical applications of this non-reciprocity of space-time modulation in metasurfaces. Non-reciprocity is a very interesting phenomena. As you see here, for example, a very interesting phenomena that you see in the interrogation room, that you see in one side, the accused person, the arrested person cannot see the cops, but in the other side, the cops can see the accused person, the arrested person. That's because this window is a sort of non-reciprocal. It can be shown that it's not totally non-reciprocal because there is a condition here. So basically, for this window to work, you should make sure that the light intensities in 2 sides of the window is different. So basically, in the room that the cops are there, so basically the intensity it should be dark, and in the room that the arrested person is sitting, the room should be quite enlightened, and otherwise the window does not work. So this is the condition that should be satisfied to make sure that this window works well. Otherwise, it would not. So what we are interested in is to realize a non-reciprocal magnetless window without any condition. So this is the aim of our study, and it can be shown that space-time modulation can help us to realize the structure. Still, it's a preliminary results and should be studied at different frequencies. What we do is we realize it at microwaves, but there are other groups that are working on optical and higher frequencies. And here, is the result of the FDTD simulation that we achieved from the numerical simulation results that you see. For the forward incident, the wave is transmitted to the other side of the metasurface to the top. And as you see, we have generated different frequencies. And here, actually, on top of the structure on the left side, I show the spectrum of the transmitted wave as well. And as you see, we have a strong frequency generation here because the modulation amplitude is strong. However, since the structure, the metasurface is unidirectional, is non-reciprocal due to the unidirectionality of the space-time modulation, if we impinge the metasurface from the top in the backward incidence, the wave goes through the structure and is transmitted to the bottom of the structure without significant generation of a space-time harmonics. So this is quite interesting. So it's a unidirectional structure. In one direction, it generates a strong space-time harmonics, time harmonics, but in the other direction, it does not. And we are going to use this phenomena to realize different structures and non-reciprocal devices. One of the devices that I studied is this space-time diffraction gratings. Conventional diffraction gratings are reciprocal and provide spatial diffractions. So basically what we have on the conventional case that you see on the top, so the incident wave is green and the transmitted waves or diffracted waves are green as well. So they are all at the same frequency. We have no frequency generation. Also, we have a symmetric diffraction, as you see, with respect to the x equal to 0 line. And so it's quite and fixed. You cannot change it, actually. For the conventional case, you cannot change the diffracted waves, and because the diffraction grating is fixed and is designed in a constant manner. But on the bottom, you see the space-time modulated diffraction grating. As you see, you could have quite different functionalities and applications and phenomena, as you see here. First of all, it's not symmetric with respect to the x equal to 0. Second of all, so basically you have frequency generation. Each diffracted wave includes different time harmonics. And also, more importantly, you could change the parameters of the diffraction grating because this space-time modulated diffraction grating is realized through a RF bias. So if we change the RF bias, we could have a different diffraction grating, different parameters, and we could have a versatile diffraction grating, which provides much more complicated diffraction than the conventional case. I will show that we could come up with a very interesting idea for coding and other purposes using this complicated and also versatile space-time diffraction grating. Here, you could analyze the structure using this wave vector diagram, which is very interesting and also complicated. But one could not analyze this diffraction grating, space-time diffraction grating, without this wave vector dispersion diagram. As you see, this diagram provides all the details for the diffracted harmonics, each spatial and temporal harmonics, and it's quite powerful for the analysis of the structure. So if you are interested, you could take a look into the paper and see all the details of the diagram. And here you see the structure is actually shined with a wave from the left side, and the wave goes through the structure and it makes a transition to all the space-time diffractions. And as you see, each harmonic is transmitted to a specified angle of transmission. Here you see that the smaller frequencies are transmitted to the bottom, and the larger frequencies are transmitted to the top of the figure. It's very interesting and shows. And if we take a closer look into the results, we see that each of these time harmonics includes an infinite number of spatial harmonics. So it provides a quite powerful pattern that can be used for coding applications. So here I showed that you could have a transmissive as well as reflective diffraction gratings that can have different applications. And also this is a very advanced applications of these space-time diffraction gratings, that you could have a multiple access system that are composed of different transmitter and receiver pairs. So basically, each receiver and transmitter can communicate while they have a same diffraction patterns. Otherwise, they cannot. So, as I said, we could change the diffraction of each transmitter and receiver and make sure that we have a desired communication between the desired pairs. And yeah, I mean, this is a very interesting application of this diffraction gratings that showed that we could use this diffraction, space-time periodic diffraction gratings for coding applications. And as I said, the interesting actually feature is that you have a versatile feature. So basically, you can change the pattern in real time and make sure that you're communicating with the proper pair. Another device that is proposed is this unidirectional beam splitter. It can be shown that if we choose a proper modulation frequency, here, for example, I chose the modulation frequency to be twice as large as the incident temporal frequency. And the incident frequency is impinging to the metasurface at 45 degrees. And it can be shown that the transmitted waves are split, and they are actually transmitted at two different angles, which is quite interestingly, is very similar to what we have in in beam splitters, in conventional beam splitters. However, here, so it's the structure is versatile. You can change the parameters of the structure, and more importantly, you have a unidirectional beam split. So basically, you have from the left side, you impinge a structure, you have a split of power, and when you impinge a structure from the right side and from the top, you have no power split, and the wave goes through the structure without any significant change. So it's a unidirectional beam splitter. Also, this one, I mean, if anyone interested, I mean, fabrication and proof of concept of this idea is quite interesting. I didn't have time to do it, but it would be very interesting to do it and show it practically. Another application is this non-reciprocal-Beam Metasurface that in conventional antennas and metasurfaces, the transmission and reception beams are similar and quite identical. We are transmitting and receiving from the same angle of transmission and reception. But what we are interested in is to have a transmission and reception at different angles. So basically what we call it is non-reciprocal beam radiation. We have different beams for reception and transmission. And it can be shown that with the proper design of the structure, this space-time modulated structure, we could have this phenomena. So here, what we are interested in is a non-reciprocal phase shifter. We are going to realize a metasurface which includes a non-reciprocal phase shifter, gradient non-reciprocal phase shifter, and based on that, we could design a non-reciprocal metasurface. I mean, if anyone interested, just take a look into the paper, all the details and mathematical modeling and simulation. And here is the unit cell of that we fabricated, and here's the equivalence circuit of the unit cell, which is formed by 4 varactors. We have different sets of phase shifters to realize the gradient, phase shifting, and also pi phase shifts, and so on. And here is the complete structure that we realized. So it's a multi-layer structure, and also this is a fabricated structure to have different beams. And as you see, for the transmission, we have a transmission beam at the 45 degree in the right side, and we have a basically reception RX beam at the minus 27 degrees. And yeah, I mean, it can be shown that we can have this non-reciprocal beam radiation using these metasurfaces. It can be also used for antenna radiation as well. We could have same scenario for antennas, but here we were more interested in the metasurface application, that we have a 2-sides metasurface, but same scenario can be applied to an antenna case. And I mean, the last part is transistor-loaded space-time metasurfaces. These transistor-loaded metasurfaces, they act as a space-time interface. So far, I just provided the results for sinusoidal space-time modulation, which is quite interesting. But these transistor-loaded metasurfaces, they are not sinusoidally modulated, but it's quite interesting if somebody do that, you know, to modulate the RF to DC bias of transistor using a sinusoidal or time-varying signal. And I have not seen that. It's quite interesting, and this is something that I would do in the future. But if anyone interested, it would be very interesting. But for the sake of this, presentation, I just go through the interface case. So here we have a metasurface that is turned on at t equal to 0, and I mean, before t equal to 0, it just reflects reflects back the incident wave. But as we turn on the metasurface, the transistor, we have a non-reciprocal transmission of the wave. So if we impinge a wave from the bottom, it goes through the structure with possible amplification. But when we impinge the wave from the top, it doesn't go through the structure. It reflects back or be absorbed by the metasurface. And we fabricated the metasurface using transistors, and you see that it provides non-reciprocal transmission, amplification in one way, in forward case, and attenuation in the opposite case. It's quite interesting, and it can be shown that this is equivalent to a space-time interface. Also, another application that we recently proposed is a reflective beam steering metasurface. It provides amplification as well as beam steering, and also full duplex transmission and reception. It's quite interesting. It can be used for wireless applications in cellular, satellites, and so on. And here's a structure which is composed of different chains, and each chain is consisted of interconnected patches, amplifiers, and gradient phase shifters. Again, if anyone interested, you could take a look into the paper that is written in the below, and you could have just see the details. And here you see that we have in the right side of the page, you see that we have iterative transmission and reception at each microstrip patch that provides a desired beam steering and amplification as well as non-reciprocity. And here's a fabricated structure and experimental setup and so on, and numerical simulation. Just a very quick simulation in MATLAB. And also here you see the experimental results that we did in the lab, and you see that we have a full duplex non-reciprocal amplification and beam steering. You could have different waves. And so basically, so this is just a proof of concept for the metasurface. And so this is interesting. Metasurface is active and provides several features, like, as I said, again, full duplex amplification, non-reciprocity, and so on. And it has a lot to be studied still. So if anyone interested in terms of modulation of the modulation of the metasurface, so it could be very interesting to see what would be the results of this modulation, or other, I mean, programmability and so on and so forth. So the last one is a programmable metaprism that you see here. In conventional prisms are like this. So you have a white light that is going through the structure, and in the output you see the spatial decomposition of the wave. And each color is transmitted to a specified angle of transmission. Basically, is a prism functionality that corresponds to a spatial decomposition of the components of the light. However, so basically this structure is reciprocal. It's not versatile. It's fixed, and also so is reciprocal. And what we are interested in is to have a non-reciprocal, and also is not lossy, and we have more control over the output rays. So we suggest this metaprism that is unidirectional. When we impinge when we shine the structure from the bottom, it goes through the structure, and it provides a spatial decomposition of different components of the wave. And when we image the structure from the top, it doesn't go to the structure, so it's a non-reciprocal, and it could have different applications in practical scenarios. It could be programmable, and because you could just control the structure through the DC bias of transistors. And here you see a proof of concept of the structure using metasurfaces, transistor-loaded metasurfaces, and so basically this is very interesting. And honestly, this is a structure we did in the lab. We didn't know, but as we went through it, we realized that it provides such an interesting prism functionality, and it's very, interesting, and still like other topics, still very young, and there is a lot to be studied, and just make it more mature. And yeah, if anyone interested, so can just, there are a lot actually to add to this metasurfaces. And in terms of modulation and different schemes, for example, you could add frequency variation, frequency change, and conversion, and so on and so forth. And here's the architecture of the unit cells that it includes amplifiers, basically spatially gradient, frequency dependent amplifiers, as well as phase shifters that provide this prism functionality. And here is the experimental results that shows that each component is transmitted at a given angle of transmission at different angles, and it's very quite similar to prisms, but it's unidirectional. And the conclusion, before I conclude actually the presentation, I would like to just talk a little bit about the industry part that is actually for commercialization of the structure. It's Tandem Launch is a well-known incubator in Montreal that is actually working on these metasurfaces and lattice intelligence. Mr. Gessimran Sethi is here, and he's working actually actively on these metasurfaces. He has done a very good job, and they're progressing very well, and so it's very promising. So basically, you could you could just make a significant advancement like programmability, and maybe just make it more suitable for millimeter waves and so on and so forth. There's still a lot to be studied, and it's still under study. And here is the profile of the lattice. They are actually they're growing, and if anyone is interested, I'm sure that they're willing to just talk to you, and perhaps for the internship, for like I don't know, just short time or long time. Just talk to them, and it's a very good company. They are in contact with big communication companies around the world, and to make sure that these metasurfaces are connected to the industry part, and it's very promising. And I myself, I'm still studying, I'm still learning to make sure that we make a good progress and make a next generation of telecommunication systems. And is a conclusion of my talk. So basically, we talked about the space-time metasurfaces, analysis and dispersion diagrams, as well as scatterings of the space-time metasurfaces. And so basically, we showed some of the interesting applications. And yeah, if you're interested, just take a look at the papers, because for each paper, there is a deep analysis and the mathematical modeling and all the details. And thank you so much for attending this presentation, and I would be happy to answer your questions.
Thank you very much, Sajjad. That was very interesting to look at space-time metasurfaces details, and both from the analytical aspect and the application aspect. So thank you so much. If anybody has a question, they can definitely write it in the chat and we can read it, or you can unmute yourself and ask it yourself. So does anybody have a question? Okay. So we have one question here. So they have actually two questions. What's the difference between the surface wave antenna in slide number 21 and the Leaky-Wave antenna in slide 22 that makes the former reciprocal but the latter non-reciprocal?
Very interesting. So the latter is non-reciprocal as well. I mean, they are both non-reciprocal in a sense, but so it's quite different. So the Leaky-Wave antenna structure is an antenna inherently. So it's an antenna that we have implemented a space-time medium on top of it. So basically, we have a spatiotemporally modulated Leaky-Wave antenna. But so it's interesting. So it's a two-port structure, but from the physical point of view, the first one, Antenna-Mixer-Amplifier, which is a surface wave structure, it's just a space-time medium. It's not an antenna per se. So we showed that this space-time medium can act as an antenna. So if we just provide the desired space-time parameters and make the structure to generate the space-time surface waves. So yeah, that's the main difference, that the Leaky-Wave structure is an antenna per se. So basically, we modulated the antenna, but the latter one, the surface wave one, is not an antenna, but it provides antenna functionality as well. So it's very interesting from the physical point of view, because it was the first time that was shown that the space-time medium can act as an antenna. I mean, it's very interesting.
Nice. So there is another question. Is it required to synchronize the phase of the sinusoidal modulation with the phase of the incoming signal in any of these applications, or no synchronization is needed?
Right. I mean, for these applications that I showed, no, we don't need it in general, but there are other actually transmission line space-time modulated that I will present in IMS in the next month that are very sensitive to the phases actually, and they are working based on the phase of the modulation, which matters a lot. So on that cases, we have to just control the phase of the modulation. But in most of the applications, no, I mean, it's quite powerful, and we just need to control the amplitude of the modulation, not the phase. It's not so sensitive to the phase of the modulation.
Okay, nice.
Thank you, Ayman.
Thanks. Any other question?
I had a question. So I was looking at, I guess, the very first space-time medium that you presented, and you were talking about using varactors and how you would have like a modulation signal that modifies the capacitance of the varactors, and that's how you end up with a space-time modulated medium.
Right.
If you're using a system like that, and you have, do you use a system like this to create like the space-time modulated antennas or things like that? And if you do, does that second frequency that you're using, so the non-modulation frequency, does that interfere with the modulation at all, or is that not a concern that you have to worry about?
So this is very interesting actually, because from the practical point of view, you should make sure that you have a desired actually functionality. So basically, you have to make sure that the modulation signal is modulating varactors. Varactors are modulated by the RF bias, the modulation signal. They are not actually, they are not varying through the input signal. So they should be invariant in the sense of the input signal. So this is important. And also, since the RF bias is much stronger than the input signal, so you should make sure that the input incident wave is not modulating the waves. And yeah, I mean, for real scenarios, this is what I do actually. And so this is a space-time modulation, but for metasurfaces, for the most part, is sometimes just a time modulation. So we don't need to send a wave to propagate all the, way through the structure. We just need to modulate one varactor for us. In some of the metasurfaces that I fabricated, we are just modulating one varactor, which is a time modulation. It's not a spatial modulation. But since the metasurface includes different inclusions and different cells, so it's a spatial modulation per se, perhaps different depending on the structure, but we don't need to. But for transmission lines, sometimes we need to just modulate it spatiotemporally and make sure that the wave goes all the way to the structure. but as you said, exactly, I mean, what you ask is very, I mean, any of this could be a new project, new research topic, if you just make sure that the varactors are working. I mean, they are actually experiencing both signal or one of them. But for the most part, you should make sure that the varactors are just varying using the RF bias, and they are not I mean, they are not varying using the incident signal.
Mm-hmm. Cool, thank you.
Right, thanks.
Okay, we have another question from the audience. They're thanking you for the nice presentation. And then would you please explain more about the necessity of using numerical methods for simulation of meta structures in your works and shortcomings of EM simulation software in analysis of metasurfaces?
Right. It's very interesting, and actually, this is perhaps they ask me a lot in conferences, and see, because it's not easy. You want to just simulate it, and so I talked with the Council Multiphysics representative in a conference, and they showed me that they could actually simulate this space-time modulated structures in Council Multiphysics. I didn't do it myself because I didn't need it. So basically, I implemented my own code. But I'm pretty sure that it could be done in Council Multiphysics as well, which is a very powerful commercial software. But so basically, I explained the procedure for numerical simulation in two of my papers. If I mean, I showed it in the slides, and so you could go through it and see. But I mean, generally, it's not difficult. It's a very easy process, because for conventional FDTD simulations, you have a fixed permittivity. But here we just need to make sure that the permittivity is changing in time. So we have different time steps and spatial steps, and we just discretize the Maxwell equation for each time and space, and make sure that it's just doing this solution of the electromagnetic waves at different times and spaces. It's quite similar to the conventional case. Just need to change the permittivity to this spatiotemporal modulated permittivity, and just because this is what we have here is continuous, so at z and t. But in numerical simulation using FDTD, you have to discretize the time and space and emulate this continuous space-time modulated medium. But if anyone has any problem, just drop me an email, and I will be happy to just elaborate on the procedure, the numerical simulation procedure.
Okay, I guess thank you very much for that answer. And I think Gursimran wants to ask you a question, and then Amir Bahadur.
Sure, thank you. Yes, Sajjad, thank you for the presentation. Very engaging. So I have a question about the metaprism. So the frequency dependence, I have two questions actually. So what causes the refracted angle to be so heavily dependent on the frequency? So that's my first question. Like, what is the mechanism that causes this frequency dependence of the spatial angle? And the second question is this a function of the incident angle as well? So for various different incident angles, do we get different refracted angles?
Right, very interesting question, very interesting. So what we have here in the right side, as you see, in the right side, we have this metaprism. So basically, if we just consider the forward case that we measure metasurface from the bottom, so we have two things: the transmitted wave. So we have the angle of the let's say the red line, which is the reference one, and also we have this the difference between the angles of each component. Okay, first of all, what causes this prism functionality is the nonlinearity of the transistors. So if you look at the transistors, we have actually different phases for different frequencies. So first of all, this prism functionality is depends on the phase that we have in the transistor, which is nonlinear. And but we have another things here that is basically the reference that we have here that can be changed using this gradient phase shifters. The reference can be changed using gradient phase shifters, but the prism functionality is basically based on the nonlinear phase of the transistors. And also, sure, if we change the incident angle, we would change the reference actually. We change the reference angle. The red one, it would be different, but I would say the difference between this component would still be, I mean, pretty much same, you know. Yeah.
So just a follow up to that is, if we were to choose a linear transistor, because in a practical sense, this might not be the most beneficial. I mean, I'm sure from a physics point of view, this is definitely very interesting. But from a practical standpoint, if we have a usable bandwidth of a signal that's like 40 megahertz or 100 megahertz, then you're basically scattering away all your power in different directions. And maybe that's a good idea for a multi-beam antenna or something like that. But if you were to target the beam towards one particular user, this becomes really difficult. So then suppression of this effect can probably be done by a linear amplifier, like a more linear amplifier, or relatively more, even in a phase range.
Right. Also, we showed in the paper that this is also due to the reflection inside the structure as well. We have two amplifiers and gradient phase shifters, and this reflection inside the structure creates this nonlinearity. Actually, it strengthens this nonlinearity. So basically, if you use, for example, one amplifier and make sure that the reflection inside the cell is suppressed, you could make sure that you have quite a linear transmission and linear phase. So basically, it's due to the reflection inside the cells as well. If you look at the cells, we have two amplifiers and one phase shifter between them, and you have multiple reflection that creates this nonlinearity, basically. Yeah.
Mm-hmm. So if we allocate most of the amplification to one amplifier instead of using two amplifiers within one unit cell, do you think that effect could be suppressed?
Yeah.
Okay.
Yeah.
Interesting.
Yeah. Thank you. Good question. Very good question.
Okay, I think Amir Bahadur has a question for you, and this would be the last question of this talk.
Hi, thank you very much for the great talk. I really enjoyed it. I just have a question about either a slide 39 or 40. I'm not sure about the slide number, but as I've written in the question box, what do you lose when you use the Metasurface? I think this one, yeah. In terms of, I'm talking about in terms of loss, when or efficiency, what do we lose when we use this Metasurface? Thank you.
You mean active metasurface or transistor loaded metasurface?
I'm talking about this one, this is the active one, right?
This is active. So this provides amplification as well. We have amplification in the desired direction.
Okay.
This is very interesting. So because always when you talk, for example, I talk with biomedical staff or other majors, and they say, okay, metamaterials are lossy and so on and so forth. But if we show that they are not lossy, even they can provide amplification. So it's quite interesting, and they could have lots of applications, because conventional metamaterials were lossy, and they're working based on resonances and so on, and they're lossy and they're narrowband. If it provides broadband applications, amplification, and unidirectional, so it just strengthens the application. So we could have it for different applications, and there are different features. Yeah.
Okay, thank you very much. So what you're saying is that this one not only does not lose anything, but also amplify the wave, right?
Right. Yeah.
Okay, great. Thank you very much.
Thanks so much.
Okay, thank you very much. Please join me in thanking Dr. Taravati again for this interesting talk, and thank you everyone for joining us today.
Thank you so much, Marinas, for this opportunity, and it was great. Thanks.
Okay. Thank you. Just going to stop the recording.